Thank you, thank you. Okay, so we are starting to understand some of the results on flat bands. Obviously, there's many results by many people, including many people in the audience. So I apologize if I can't show all of them. But one result is that a flat band in a magnetic field brings up the Berry curvature as the non-linear Berry curvature as basically the spread of the flat band in first order in field. And as actually Dima pointed out during lunch, this is actually just some sort of a magnetization. That's orbital magnetization. There was, you can relate it. Basically, it's kind of the same formula, but to some orbital magnetization that was pointed out by Shan Yu. But really, this is really manifest in a flat band because this is the only term you're going to get in a flat band if you apply a magnetic field. Nothing else exists. Okay, so now let's see how the Fubini-2D metric shows up in flat bands. Okay, so there's some results that I'm quoting here, and really a person who was seminal in finding these results is Päivi Torma, and these results are much earlier than the subsequent work that I'm going to show you here, in some of which I was involved too. So Päivi basically proved that in mean field, i.e. with a order parameter put in by hand, which is what mean field does basically, this order parameter can be superconducting, can be spin density wave, etc. Then if it's a superconductor, the superfluid weight is basically proportional to the gap, this is delta, to the filling of the flat band. So if you have full filling, then you've got nothing because it's just a flat band, so it's zero. If you got zero filling, you also have nothing, but then it goes kind of like this. So these are terms that, you control, but then fundamentally you get the Fubini-2D metric here. Okay, and this is a mean field calculation, and it comes by taking the derivative of the free energy with respect to momentas at finite wave vector. Okay, this relation actually is not fully correct in the sense that Päivi and us basically found out there's something called the minimal quantum metric, which I won't get into, but it's some quantum metric that you have to kind of find this minimal value over positions of orbitals in the lattice. I'm not going to get into that because that's too complicated. But roughly, this is what it is. And in Ginzburg-Landau, if I have a flat band, as was pointed out in the previous session, most flat bands in Ginzburg, well, all the flat bands in Ginzburg-Landau, as we knew them, they were not topological, so they were described by a parameter called the mass, and the superfluid stiffness basically was becoming 1 over the mass. So in flat bands, if you don't take into account, the fact that you get quantum geometry, you get wave functions which change, maybe some topology. Flat bands basically are localized, and the superfluid weight should be 0, which basically means that that's a pseudo-gap phase where if I put some pairing, all I'm going to do is take the spin up, take the spin down, form a spin singlet on site. That spin singlet is going to stay there. It's going to cost you to break that spin singlet, but it's going to stay on site because it has no hopping, i.e. its mass is infinite. That's not a superconductor, obviously, because it's a superconductor with a Goldstone mode that's got no stiffness. And basically, that tells you that if you have localized bands, the most you can get is a pairing gap that's on site, and we can call that the pseudo gap. But the band-load delocalization, which appears here, provides finite stiffness. And now, basically, what I'm going to show you is you can make more, so you can argue, well, you got mean field on a flat band. Is it really true? I'm going to show you that in some models, albeit contrived models, which I won't, try to justify physically, you can make statements beyond the mean field and obtain some exact results. Okay, so for example, these are the type of models that you can obtain exact results. So what we do is we take a flat band, and we consider the gap to every dispersive band to be infinite, okay? First approximation. Second approximation is you project all your interactions into flat bands. So if I didn't project all the interactions into the flat band, and I just consider, say, I just had one band, and I consider a one-band Haber model with no kinetic energy, that will be exactly solvable. It's a classical model. All I need to do is tell you the configurations of particles on site. The insolvability of the Haber model with nearest neighbors comes from the fact that the kinetic part and the potential part don't commute. Okay, but if I just have the Haber model without the kinetic term, i.e. a flat band, trivial flat band, for example, then that's exactly solvable. It's a classical model. Now, this Hubbard Hamiltonian that we have here, when projected to the flat band, is the projection to the flat band is the only thing that makes it non-trivial. And we're going to start with this contrived Hamiltonian. We're going to start with this Hamiltonian, where we take the Hamiltonian to be the projected density on site R. Alpha is the number of orbitals, blah, blah, spin up and down minus n, okay, and project this into a flat band. The projection basically comes into this bar projected operators. Okay, so so this is the first contrived thing. The second contrived thing, which is actually turns out to not be that contrived in the end, is that we're looking for systems which have a uniform pairing condition, meaning the orbitals, this is basically n alpha is the sum over k of the projector into the alpha band. This is kind of the occupation of the alpha band, of the alpha orbital in the flat band. Sorry, so this is orbital. This is the projection into the flat band, single particle projection into the flat band, and this is the number operator. This is n alpha, and basically what we want is that this does not depend on the orbital alpha, and this is called whatever uniform pairing condition. Basically, why this is not contrived is if you have any lattice symmetry. For example, if I have the graphene lattice with A and B sublattices and spin up and down the AB sublattices, the C2 symmetry of graphene, or the C6, basically maps the A into the B sublattice, and you've got this by default, by symmetry. So it's not a contrived condition on some lattices. So we're going to work on those lattices. And this Hamiltonian, when you expand it, you notice that it becomes up to a total chemical potential term, the negative U-Haber model. Okay, it's negative U-Haber model. So it's likely it'll superconduct, right? It's got some other sickness in it that I won't talk about, but this will have some superconductivity. Now, what you can notice is that this is again a positive semi-definite Hamiltonian, and every time you find these Hamiltonians like quantum Hall ferromagnetism and these Hamiltonians that have exact, they're non-trivial, but they have exact ground states. Their solutions come from positive semi-definiteness. You basically know that the spectrum is positive semi-definite, it's a square, and you're going to be able to find the zero energy ground state, the zero energy state. So then you know it's a zero energy, it's a ground state. So you found the ground state. Okay. So this is what we're going to talk about. It's very easy to find the ground state of this because it's a zero, it's a positive semi-definite Hamiltonian, and then it's easy to find the ground state of this, which is a negative U-Haber model. Okay. And the ground state is the following. You notice that if I create, all the bars are creation operators in the flat band, in the projective band. If I create an electron with spin up and an electron with spin down, this term is zero. Okay? So this operator, which creates a sum over all sites of electrons with spin down and then electrons with spin up summed over the orbitals, is going to be, if I apply it to the vacuum, is going to raise the number of particles in the vacuum, so I can form any number of particle ground state, and is going to be a zero mode of this guy. So it's a ground state. Okay? This is related to the eta pairing operator of C.N. Young, but it's not really at momentum pi. It's a bit of a different eta pairing operator, but it's just a small generalization. So now I know all of these are ground states, and of course, as you can see them, they're just paired ground states. Okay? They're superconducting paired ground states of the system. Now, the other thing that happens in these quantum Hall ferromagnets, which is kind of neat, it happens in projected twisted bilayer graphene, it happens in quantum Hall ferromagnetism, is that once you find the ground state, right, it's a huge number of particles ground state, but because you've got this positive semi-definiteness, you found an Avogadro number of particles ground state, right, which you're not able to find usually in many body systems. But here you found it, And then the excitations above these ground states, solving for them becomes a single particle problem. So if I want to solve for the excitations, the n plus, in this case, the two particle excitation, because I want to look at the Cooper pair, the two particle excitation above the above the ground state to show the superconducting basically, that's a solvable problem. That becomes, and in fact, that just becomes a one-body problem. You would say it's a two-body problem, but like there's reasons why it actually becomes a one-body problem. If I try to solve for 3 excitations above the ground state, it would become a two-body problem. 4 excitations would become a 3-body problem, etc. Okay, so the moral of the story is the following. After you do a bunch of algebra, okay, you find out that the two-particle excitation, okay, has, in this particular model, because it's contrived, in most models like TBG, it has a dispersion, has a continuum of states which are the BDG quasi-particles. They have a gap. The gap, this is the superconducting gap. It takes some energy, equals to twice to the gap, to break a pair, because the ground state is paired. So it takes an energy twice to the gap. In this case, it's actually flat, because the energy of one BDG quasi-particle is U. For some reason, this doesn't have to be flat. Okay? Now, the interesting thing is that now you've got bound states. And normally when you we're not doing mean field here. So when you don't do mean field, the way you find superconductivity is not by putting, not by working in number non-conserving formalisms like BDG. The way you do in mean field, you basically, if you were to do numerics, for example, the way people test numerics in the Hubbard model, they diagonalize the Hubbard model, they look at the particle spectrum for n number of particles, then they look at the particle spectrum from n plus 1 number of particles. From that, they get the pairing gap, what it would be to excite one particle. They take twice times that pairing gap, which would be to excite 2 particles, and they ask, do I have a bound state below the 2-particle continuum? Okay? If I have a bound state below the 2-particle continuum, meaning I now look at the spectrum of n plus 2 particles, and I can identify the continuum, it screams at you, because the continuum, the incoherent superposition of quasi-particles will just add up the energies. I can find a continuum. If I have a bound state, then the system has a superconducting instability. It's called the Richardson criterion. So this is what we do here, and you can solve for this exactly. And you find, of course, that this is a perfect superconductor in the sense that the bound state, as you can see here, goes all the way to 0 energy. And that's easy to see because I've told you before that all of these are ground states, you see? So if I go to n plus 2 particles, it's a 2-particle operator. If I go to n plus 1, okay, I added 2 particles, but that's going to be a ground state too. So I better have a mode that's exactly at 0 energy. Okay? But moreover, what you see is that it's got stiffness. And the stiffness is actually the mass here. Okay, that's the stiffness. That basically prevents the fluctuations of the order parameter. This is the order parameter. And what you can prove is that the energy spectrum around here is given by this. Okay, Gij, Pi, Pj. With actually an energy factor of U here, which I didn't put. So Gij, Pi, Pj is the energy spectrum around here. So now you can see that the meaning of the superfluid stiffness is basically like the Cooper pair mass, but you can see it clearly coming from here in this model. This is the Cooper pair mass, and non-zero superfluid stiffness, with non-zero quantum geometry or non-zero Fubini studiometric, which comes from not having fully localized states or having topology, in which case it's bounded, give you non-zero, gives you a bound for the Cooper pair mass. Okay? Questions? Okay, very good.
So, these are not the usual quasi-particles, but the quasi-particles.
These are the quasi-particles. These are one particle. These are basically coherent superposition of 2. If I was to take the commutator of this with 1 fermion, I would get U times 1 fermion. So these are 2 Bogoliubov quasi-particles, two broken pairs, right? And then I have a bound state with binding energy exactly twice times the gap. That's a perfect superconductor, right? If my bound state, so I have, so my bound state has, I managed to lower the energy by forming just the Cooper pair bound state.
So the reason I'm asking, how do you see that this does not violate this Landau criteria for superfluidity, right? You need to have minimum for epsilon divided by p. Then your superflow is stable. This obviously does not have that. But I think it's just something different. But,
I think the Landau, so I'm not sure that the Landau, so I think the Landau criterion might need to be, you mean because it's quadratic or what?
Yeah, exactly.
Yeah, so the reason why is I think all these Landau criteria, etc., might need to be revisited in flat bands. So I have two comments here. If you add dispersion, it'll acquire a low energy linear part.
That would be fun.
Right. Yeah, exactly. So if you add dispersion, it will require a low energy finite part. Now, the thing that I'm pushing under the rug here is that there's a symmetry of this model which makes a neutral mode also have a gap. So this model is in a competition between going superconducting and phase separating. And how to, so Ehresberg did some Monte Carlo on this, and you can stabilize, if you add kinetic energy terms, some terms stabilizes, sometimes make it phase separate. Depends on which terms. Unfortunately, you cannot solve the model exactly once you add those. So that's what. But I think even like these Landau criterions, the Ginzburg-Landau was done for non-topological bands, right? I think a lot of the stuff might, In other words, whenever somebody says a criterion, we have to, I think. I'm not saying that all of the criteria will be wrong, obviously, but I think topology brings new things in, especially with flat bands, because there's papers in the literature by famous people saying flat bands will have zero superfluid stiffness, right, because of 1/m, exactly Ginzburg-Landau, and that's but that's just because we didn't know topology back then, right? So it's fair enough, but I think. I'm not sure if the Landau criterion would be valid here. That's my. But the things that I have to say about those are the ones that I said.
But it stems from a very simple idea that the flow should be stable with respect to creation of quasiparticles, right? So, in a sense, it comes from energy conservation. You assume that matrix elements are always there, to create quasiparticles. So you're only limited by energy conservation. That's where you get that.
Yeah, but for example.
So it's so simple that it shouldn't matter where you apply it.
Well, but it does matter. It does make some assumption about adding, like when I add quasiparticles, right? I add them in different bound states, or it does make it. I think it makes some assumption about what kind of bound states I can have, which comes to matrix elements basically. So I think those might be a bit different here. But right now I'm just pulling stuff out of my pocket. But all I'm saying is that it requires it's not a bad idea to revisit those ideas. Okay, very good. So, relevance to TBG. Now, take this with a big grain of salt, or big. So you have to be cautious with interpretation. But for example, critical current measurements, they were done on TBG, claim, and I'm not making a claim that this is true. You can go read your paper and make your own claim. I actually think much more experiments are needed. Claim that in TBG, the correlation dominated superfluid rate comes from quantum geometry. Now, I think that, I think that this is one of these cases where you cannot have just one paper about it. But go read the paper if you want, and think of ways to propose other things that are more clear, that will show that TBGs from the twisted bilayer graphene superconductivity has something to do with quantum geometry. I personally thought it has, then I didn't think it has, then now I still don't think it has, because TBG, the quantum geometric effects show up only when you have 10 millielectron volts bandwidth. I'll come to your question. When you have 10 millielectron volts bandwidth, above 10 millielectron volts, the kinetic effects take over. Moreover, I think there's more and more evidence that basically what's important there is the correlated bands, which have much larger bandwidth. So the interacting bands have much larger bandwidth, which you wouldn't see in the non-interacting system. Sorry, there was a question.
Yeah, so if this superconductivity arises from flat bands, do you have any restriction to the symmetry of the superconducting gap?
No, no, it's basically what interactions you put in. So here, for example, so what would happen, so this is for S wave. If I had a different symmetry, I would have this Gij coupled, tensored into the symmetry of the order parameter, basically. So this is, you see here, I pick the Hamiltonian, so the symmetry is S wave. I could pick the Hamiltonian to have D wave symmetry, and then the Cooper pair mass would be a convolution of the quantum geometry plus the form factor of the Hamiltonian, because basically what gap you get comes from the form factor. Does that make sense? Thanks. Okay. Next example. Does anybody know what this is? This is a person's hand. It's really cool when you get this on an archive. Okay, and this is the Twitter superconductor, and I thank Jen Fercano for pointing this out to me. So does anybody know this guy? So this guy, well, he's got 2.2 million, I think this is 2.2 million views, right? That's it? 2.2 million, huh? Like basically he's more famous than anybody in this room will ever be, right? And, he's a very big proponent of this. He makes frozen coffee, and his only, basically pedigree is that he was a Princeton undergrad. And he got all this attention for this Twitter superconductor, and you can see if you follow his post how he basically marketed this, and then how disappointed he was when reality struck. But the moral of the story is, you have copper goes supposedly where lead is. We don't really know actually. If you suppose copper goes where lead is, then what the oxygen bands that were close to the Fermi level happens, they get pulled down, and you got flat bands at the Fermi level. Now, a lot of, some people made big noise about flat bands. These flat bands turn out to be very, very localized. So for example, you plot the quantum geometry, you've got nothing. Their Wannier localization is 0.2 of the unit cell. So it's good to check these things that before one claiming superconductivity, otherwise, I'd be making frozen coffee. So okay, I don't want to go through this. Okay, so I want to basically, in the last, I guess, part, I want to show you some rewriting. And this rewriting has to do with quantum geometry now in dispersive bands. So I hope I convinced you that there is something about quantum geometry in flat bands. It can give you bounds on the superfluid stiffness. Now I want to show you that it can appear on metallic Fermi surfaces and not only the insulators. And the reason why I want to point this out is that usually we think of quantum geometry that being only important in flat bands, and whenever you have kinetic effects, basically these overwhelm the quantum geometry. While that's that can be true in some cases. If my Fermi surface has topology itself, the quantum geometry can be quite high. Why? Normally, as I think Fuan mentioned this, these effects are huge, and the reason why they're huge is they have to do, topology and quantum geometry have to do with derivatives. And if I take a derivative of something that winds, something that makes a 1 around, a circle, right? The derivative of k, like k winds, for example, right? From 0 to pi on a torus, the derivative of k is going to be 1. 1 is a huge number. Integers are huge numbers, right? So basically, the effects, if I have a Fermi surface that has like a Weil point or like a Dirac node, etc., I expect these effects to be quite large. That's an expectation. Okay, let's see how that expectation fares with reality. And let's look at the electron-phonon coupling. This was actually the opinion of referee A about this work. So the electron-phonon coupling, you'd also expect it to have something to do with Wannier localization, right? Why? At least in some sort of a frolic type electron-phonon coupling, where the phonon is just the displacement of the atom from the equilibrium position, and the electron-phonon coupling comes from expanding the hopping of the Hamiltonian matrix with respect to the position, to the displacement in the position. Then in that case, it becomes very clear that you'd expect a lot more variation or a lot more electron-phonon coupling for delocalized bands. Why? Because, well, they overlap more. If they overlap more, you take derivatives, things change more than by just having localized states. Okay? Now, there's another type of electron-phonon coupling that's not Froelich, that's basically Holstein, that has couples to the density, that I won't take into account here. And different materials have different contributions of these. So I want to show you a simple model that makes it clear that this quantum geometry comes into electron-phonon coupling in dispersive systems. So for this, I need two approximations. One approximation is what we usually do in tight binding models, and this is a two-center approximation, okay, which tells you that the hopping between two atoms depends only on the distance between two atoms. I have one atom at position R1, one atom at position R2. I also move them a little bit, this is the phonon field, a little bit from position R1 and a little bit from position R2, with the implicit agreement that U is much smaller than R, and I can expand in U, but the hopping is just dependent on the difference. It's called the two-center approximation. Now, in superconductivity, people usually look at the Macmillan constant, lambda, which is basically defined as, proportional to some sort of average phonon line width. What is this average phonon line width? Well, is the integral, okay, over the Fermi surfaces of this quantity. Okay, this looks kind of impressive, but it's really just saying some very simple facts. It's saying that if I, compute for n and m being bands, Pn is the projector into the nth band or the nth Fermi surface. Pm is the projector onto the mth Fermi surface, and F are some electron-phonon couplings. So what's this coefficient really? If you don't consider polaronic effects, etc., this coefficient gives you a bound for the TC. And the way you get it, this bound, is what you do is you have an electron-phonon coupling Hamiltonian, you have electrons, and then you perform a Schrieffer-Wolff transformation to get rid of the phonons to first order and rewrite your Hamiltonian as an electron-electron Hamiltonian. And that becomes the famous BCS Hamiltonian when I consider only some momentum channel. It gives you a negative interaction. That's the famous, way we understand how to get electron-phonon coupling superconductors. And this is the quantity that's going to come in, okay, in that, because you see, second order, the Schrieffer-Wolff transformation gets rid of the phonon at first order and introduces a second order electron phonon, which is basically this. And this is kind of the interaction. So basically, you can imagine that the TC has the interaction in it. So this is roughly the Macmillan constant. This is roughly what it physically means. It's a kind of a measure of the pairing in your system, or of the electron-electron interaction after you integrate it out the phonon. Okay, which phonon here, phonon here. Okay, and these are projectors into the Fermi surfaces, and this you're going to take an average over all the Fermi surfaces. So now let me show you why that's actually dependent on the quantum geometry. And it's a very easy thing to do that basically kind of makes this scream out at you. So the first thing to do is to realize that building models that are complicated is going to give you complicated answers. You want to build a model that's simple enough, that's not trivial, that still can have the physics. And Holstein model does not represent, is basically almost never correct fully, but we still use it a lot to understand a lot of things in electron-phonon coupling. The Froelich model is more correct, and we use it quite severely, but This model here, where I basically take the hopping between two atoms and I assume that it's a Gaussian decay, okay? And this Gaussian decay will be important. Normally, it has to be an exponential decay, right? Because I have orbitals. The hopping is just an orbital overlap. This has to decay exponentially. But the power here doesn't need to be 2. That's the only approximation here, okay? The power can be something different. If I put the power 2, this will give you some beautiful expression, or at least beauty is in the eye of the beholder, but I think it's beautiful. That will give you the physics. If it's not 2, I think the same reasons will apply, i.e. derivatives in K, but the expression would be a bit different. Now, I want to point out that this approximation, for example, for graphene is exact at nearest neighbor, okay, in the two-center approximation. So it's not an approximation that's that bad for many materials, actually, and I can go into the reason why it's exact. But the moral of the story, and the reason why this is nice, is because if you take the derivative of this, it just brings one of the R's down, okay? And I know that the electron-phonon coupling is the derivative, right? I have a T of the distance between the atoms. I move the atoms a little bit. The phonon field is the movement. I'm going to expand in that, and I get this derivative. So the electron-phonon coupling is proportional to the derivative of T. But when I Fourier transform this, because I bring an R down because it's R squared, when I Fourier transform this, this becomes the derivative in K. Okay? And now I'm in business because I can do a spectral of the electronic Hamiltonian. But I can do a spectral decomposition of my electronic Hamiltonian, which just says my electronic Hamiltonian is a sum over the kinetic energies times the projectors into the bands. And if I do that, then my derivative in K gives you a derivative on E, and then plus a E derivative on the projector. Now, we know what these two parts are. We're going to label them, one of them being energetic part, meaning if my band is flat, this goes to 0, because E doesn't depend. And one of them, we're going to label the geometric part, meaning that if my band's wave function is constant in K, okay, this will go to 0. For example, in flat bands, this is 0, there's only this, okay? If I just have a single orbital flat band, which means localized, then or even with some dispersion, but it's single orbital, so the wave function cannot change in K, then this guy is 0, okay? So this is how we're going to label the two. And then we're going to compute this Macmillan constant. Now, I don't need to get you through the details because that's kind of annoying, but I'll show you the results. So first of all, I want to point out that, in graphene, actually this approximation is exact. And the reason why it's exact to nearest neighbor, the reason why it's exact is that the graphene to nearest neighbor, if you expand it in harmonics of the space group, is just one harmonic. You don't have many terms. If you expand the electron-phonon coupling, it's also one harmonic. So the electron-phonon coupling Hamiltonian is proportional to the electronic Hamiltonian, which is basically what we're saying in the previous thing. Now, it also applies quite well to radial movement of phonons, but not to angular. So if you've got angular movements of phonons, then this approximation that I've made here will be wrong. Of course, as you know, graphene has Dirac nodes, and these Dirac nodes have winding numbers around the Dirac nodes. So now I'm going to give you the results. So the Macmillan constant turns out to be a sum of two. So remember, we separated an energy part and a geometric part. So it turns out to be a sum of two parts. Part number one is purely kinetic in the sense that it's the Fermi surface integration of the derivative of the kinetic energy, okay? This is a constant, but this is purely kinetic, okay? Now, because of symmetry, there's no cross term like lambda E, lambda G, all right? So we named this the geometric, this the energetic. But I also told you that the electron-phonon coupling, then the Macmillan constant is a second order in electron-phonon coupling. So you'd imagine you could have a cross term. You don't because of symmetry, and we know the groups where you don't. Now, the geometric part is equal to this delta E squared is basically the chemical potential, right? This delta of finite chemical potential. This is mu, so this goes out. This is for linear dispersion. This goes out. Okay, so it's just the Fubini's 2D metric. They integrate over the Fermi surface of the Fubini's 2D metric. Now, I've told you that Fubini's 2D metric, when you have topological bands, is bounded from below. That's also true if you integrate the Frobenius-2D metric not over bands, but over Fermi surfaces. If that Fermi surface has a winding, for example, there is a topological part, which this is larger than. And this topological part is proportional to the square of the windings of the two Dirac nodes. Okay, next thing, values. Well, so we did some ab initio here also, which is the way you benchmark this between the ab initio. For graphene, this approximation is incredibly good. I told you it's exact. The only non-exactness comes from the fact that you have not non-two-center approximation hoppings, but they're very small. And you can see the lambda ab initio versus lambda as a function versus the Macmillan constant computed by us, computed from ab initio as a function of chemical potential. And you can see that the geometric part over topological part, basically, they're equal to each other in graphene. So roughly half of it is supported by topology, by geometry. Now, MgB2, much more complicated system, many more Fermi surfaces. MgB2 is a famous superconductor, high temperature superconductor. Well, high, it's not no LK, but everything in this happens from the boron. The phonon that causes superconductivity happens from the boron. The isotope effect happens from the boron, and the bands, electronic bands, happen from the boron. Now, the electronic bands have two parts. One of them is a pi bonding part, which comes from the pz of boron orbitals. The system is hexagonal, right? The boron is hexagonal. So that's like a graphene layer, but since you're in 3D, you're making a nodal line everywhere around, right? So that has topology, and this topology was known. It was done by Jin and Al in 2019. Now, the Macmillan contribution, the contribution to the Macmillan constant of these pi bonding turns out to be actually 7%. So it's not that large. So something else happens, and really what causes superconductivity, and this is supported by ab initio, is this sigma Fermi surface. A small Fermi surface around the gamma point, large coupling to the E1G phonon, okay? It's basically a sigma bonding Fermi surface. So now, if you look at this Fermi surface, you think it has no topology, but in fact, everything that's got a vortex will have some topology. So basically, the Fermi surface here turns out, this sigma Fermi surface turns out to have similar type of Euler topology as the bands of twisted bilayer graph, right? The Fermi surface is two-dimensional manifold, because I'm in 3 dimensions. The Fermi surface is 2-dimensional. I can define it by an Euler number. That's the topology of this Fermi surface. What it really says is that the wave function changes. As you go around the Fermi surface, the wave function changes and winds in a non-trivial way that goes in between. You have two Fermi surfaces, goes in between them, and it changes. But it's basically got an Euler number. And in the end, the same result happens, similar as in graphene. You just have two types of bonding here, sigma and pi. The Macmillan constant breaks into a sigma energetic and sigma geometric, into a pi energetic and pi geometric, and the sigma geometric, the Frobenius-2D metric comes in naturally. And this Frobenius-2D metric basically, it just comes into the geometric part. Now I want you to look at the numbers for this one, though. For this one, for MgB2, something different than graphene happens. So in graphene, the geometric part was basically half. In this guy, the geometric part makes 92% of the entire lambda, okay, in MgB2. Now, I don't claim, so I want to make two very clear statements. I don't claim that all the systems that I don't claim that quantum geometry will give you high TC. I don't claim that all systems that have quantum geometry will have superconductivity. What I do claim is that in these two systems, MgB2 and graphene, the geometric part of the electron-phonon coupling is, in MgB2, makes 92% of the entire electron-phonon coupling, and in the graphene, it makes 50%. Okay, so I'm going to stop for some questions. I think everybody it's time for siesta. but because then I have some other part that I'm going to go through in 10 minutes, but I'm basically almost done. So any questions?
So I don't know if it makes sense, but here you have related to the geometry, or you have separated the electron phonon in these two parts. But you have already integrated the k-dependence of the electron-phonon coupling. So is there some relationship between having a non-trivial geometry and maybe having some k-dependence in the coupling? I'm thinking about having some non-trivial pairing or symmetry. If there is some relation, some intuition that you can gain from...
Yeah, I mean, so, yeah, okay, very good question. So basically, here, the Macmillan constant is basically an integral. It's this average that does the integration. Now, if I wouldn't compute the average, okay, and if I would focus on a particular phonon, these are zero momentum phonons that created. So you need to know the phonon that's the strong. I'm not claiming that I know what the strongest coupling is yet. I will claim in the next slides. But once you know this, you can show that even the k-dependent one has is proportional to the Fubini metric in just locally. So because, I mean, that's also bounded by the topology, by the fact that you have Berry phases, etc. Now, just another disclaimer, all the ab initio codes, etc., like all, you know, what Ionerea and Prenea do with these electron phonon coupling, they're all correct. They all give you the correct result. They have this in them. There's nothing wrong with the codes. It's just that they give you a final result, lambda, right? And when you ask what comes, this is in a way just a rewriting, right? But when you ask what comes from where, then this basically tells you which comes. The Hamiltonian has two parts, the spectral projector, the wave functions, and the energy. This tells you what comes from one, and tells you what comes from the other, right? So that's what this does. Make sense?
Yeah.
Thanks. More questions? Yes.
Yeah, one question to this energetic contribution and the topological, which, yeah, I don't know how you define that. Is that just like from anomalous velocities?
Yeah, so here's how I define them. So when I look at the electron-phonon coupling, it separates into two terms.
Yeah.
The Hamiltonian is the electron Hamiltonian, which is just hoppings, right?
Yeah.
So I can get from the electron Hamiltonian, I can get to the electron phonon Hamiltonian. Separates to energy times projector.
Yeah, but on the next slide, you basically have three contributions.
Two. So here, normally I should have, so my electron phonon coupling, so my electron phonon EP Hamiltonian has basically an energy plus a geometric. My electron phonon, my Macmillan electron phonon coupling is basically this squared times some other projectors into bands. So it's going to be some lambda E plus lambda G plus a cross term plus lambda EG. Now it turns out that these are zero for this by symmetry for the systems that we looked at. And in some symmetry groups, given some numbers of nearest neighbor hoppings, they're always going to be zero in some symmetry groups. Okay. So then you just have the first two terms, which are these guys. Does that answer your question?
Yeah, so and the lambda topological.
Oh yeah, so lambda is the sum of the energetic one and the geometric one. Yeah. The geometric one is always bigger than this number, which I call lambda topological, because it has the windings of the Diracs. Okay. So so this is like the same bounds that you can find in flat bands. This geometric part is always larger than the topological part and the topological part has to be non-zero because these Dirac nodes have winding of the. More questions? Some more questions.
Only the radial phonons again, or also these other modes?
Yeah, so I can show you exactly which phonon this is. So it's a momentum zero in this direction. This is the phonon that creates it. Okay? This is the displacement. Okay? Thank you. Very good. More questions?
Okay, like I understand that quantum geometry somehow it measures that from k to k plus dk, maybe the block states at k tends to reside on some A atom more, but when it goes to k plus dk, like to migrate to the B atoms a little bit. Like I understand quantum geometry that it can depict such a picture. So if Fermi surface has a stronger quantum geometry, then does this quantum geometry is more sensitive to some certain phonon modes, like optical modes, that brings A and B atoms together, or just shear them?
Oh, okay. So so you're asking me, is there, so far I haven't told you, so far I brought the phonons out of the, I told you once I know what the phonon that creates so in MGB2 we know the phonon that creates the superconductivity. I told you once I know it, I can tell you what contributions are. What you're asking me is, how do I know to which phonon it couples the strongest? That's basically what you're asking me, right? And that's going to come in, well, the thing is, in general case, I don't know. There's many things, but I know it in one other case, which is some Kagome metal, which I'm going to talk about now.
Okay.
Okay.
Thanks.
More questions? Okay, how much more time do I have? Do I need to torture people? 10 minutes? Okay, yes. Okay, so the last thing that I'll talk about is the electron-phonon coupling in Kagome metals. And I want to give, basically this was started by an experiment by Santi and David, and then it involved Ian Dumitru and my postdoc Xiaolong, and the samples from Claudia Felser, who always sends us very nice samples made by Subjuhit, I think, who is here also, so thank you. This material has what I think is a remarkable CW, and this CW basically, experimentally, is found to appear at 1/3, 1/3, 1/3 wave vector. It's one of these Kagome materials, and but what is seen in Santi's experiments is that there's no collapsing wave vector here as you approach the transition from above, but there's a collapsing phonon at 1/3, 1/3, 1/2. Now I won't explain this difference because I don't, it will require too much time, but I will show you how basically based on a simple electron-phonon coupling principle that has to do with Vanier states, and that basically has to do with well, I mean, you don't need to understand in terms of quantum geometry, but you can if you want to. We can reproduce this softening of the phonon analytically, which is something that I don't think is that easy without ab initio codes. Moral of the story is this phonon comes from the trigonal tin. So here you got vanadium in the Kagome lattices. Okay, you got cadmium, which is irrelevant. Just donate some stuff. And you've got tin. Okay? And this is a tin phonon that makes, we know that it's a tin phonon. Now, how do you usually get, this is a stable material. I mean, it has a CW. But how do you usually get phonons? Well, the way you get phonons, you compute this, or like negative or CW. Normally what you do is you compute the electronic spectrum at high temperature, meaning all the electronic contributions are out. So you kind of just put the electronic temperature to infinity. Okay? And then the phonon spectrum should be all positive. And then if what we think about electron-phonon coupling and the way you get CW is correct, what happens is that you perform the electron contribution to the phonon spectrum, to the phonon energy. So basically you can put some bubble diagrams. You add those bubble diagrams to the spectrum at high temperature, and you should see the phonon spectrum going down, and at some temperature, the temperature, as you lower the temperature, the electron, the electron contributions to the energy of the phonon become more important because They have, some 1/t in them, etc., some powers of temperature, and you lower it, at some point the phonon goes, the omega squared of the phonon goes negative. So that means an imaginary phonon instability. Well, moral of the story is that what we did in this system is we know the phonon that goes negative, okay? And that's the tin phonon is at momentum pi, and is the even combination around some mirror symmetry plane. Now, we need to make an approximation for the electron-phonon coupling. And this Gaussian approximation basically in the end tells you that the electron-phonon coupling, the largest electron-phonon coupling, and this is what you ask basically, how do you sort of figure out which is the largest electron-phonon coupling, is when you couple the phonon with the electron of the same Wannier center. So it kind of makes sense in the end. That's not always true. For some, it depends if you're an optical phonon or an acoustic phonon, but so it's got variations. But roughly it makes sense that if you take an electron that has some Wannier center and then you couple it, you look at all the phonons with which it interacts and you ask which one is going to interact the strongest, it's going to be the one with the same Wannier center. Okay? So if you do this, you get a exact electron-phonon coupling, which in this material of these many atoms is very simple because we just considered the phonon that softens, and we now postulate. Then we verified it by ab initio, but we now postulate that the electron-phonon coupling is the strongest when you couple the Wannier center of the phonon with the electrons with the same Wannier center. Okay? So that gave us this very simple coupling of the electron even under this mirror plane with the phonon also even under this mirror plane. And then you compute the bubble, and you find out that in this material, this bubble, which is particular, this material has many orbitals, right? If you compute the total susceptibility, you get nothing. Okay? If you compute the orbital resolved susceptibility, you have to ask which orbitals, you get many things, and you have to ask which orbitals are correct. For this case, it's just the susceptibility of this even mode that got picked, electronic even mode that got picked by the electron-phonon coupling. If you do it, you get this type of a spectrum, which, if you leave aside the small wiggles here, is basically a nearest neighbor triangular model, okay? The susceptibility can be written as an on-site. This on-site susceptibility is going to be the one that's going to lower the phonon frequency to negative, or to omega squared to negative, and nearest neighbor. These nearest neighbor are what gives you this dispersion. Okay, so now this is the last slide of my talk. So with this electron-phonon coupling, which comes from basically considering the Wannier center matched of the electron and the phonon, which is basically, I'd like to understand it as a quantum geometric principle, but you can just take it like this. What you can see is the remarkable match between high temperature, this is the high temperature ab initio, okay, where everything is positive in the phonon spectrum, okay? And then with the perturbation that we put, which should be valid only for the lower branches of the phonons, because that's the phonon that we are looking at, that we coupled it, right? With that simple perturbation, you now see that at low temperature, you get exactly the correct phonon coming down that's in Santi's experiments. And the reason for this is that the initial phonon was flat, okay? So the only dispersion that comes in is because of the electron susceptibility. Now this electron susceptibility has dispersion. By the way, this is our perturbation, just one bubble, and this is the DFT, right? So you can see the agreement is quite good. So this dispersion is just the bubble. And how do I know that the dispersion is the lowest at the H point? Well, I know it's a triangular model. This is just, the dispersion is just susceptibility. A triangular model has the minimum at the H point. So basically, I guess the moral of the story, so this is where I want to stop, and I want to basically just point out that it's good to think in these type of Wannier terms, and when you think in terms of Wannier states and their localization properties, as were very early introduced, by David and others, basically quantum geometry comes in kind of naturally. So it's also good, you can think also in that case, or you can think it's a buzzword of basically understanding Vanya states, but whatever you think, looking in terms of these type of formalisms can lead to good results in terms of materials, quantum materials phenomena. So thank you, and questions maybe?
Yeah, thanks. Could you repeat how this, like the phonon or like the Vanier center is selected? You said like the phonon, like from the tin, you said it's pi order, right? But I assume 0, 0 pi, right, out of plane?
Yeah.
But I guess from the Kagome letters, the Vanier centers are kind of moved in plane. So like, how does this?
So that's another thing. So this coupling is only the coupling to the Vanier centers of the tin. Okay. So you're basically just taking, this is a tin phonon. Okay. You couple it. The assumption is this tin phonon is going to mostly coupled to the tin. Okay. So these are tin operators. But now you're asking which combination should I take of them, right? And where's their Vanier center? So there's two different combinations, and so the Vanier center can be within the unit cell or between unit cells, and you take the one with the Vanier center within the unit cell where the Vanier center of the phonon also is.
Okay, and if it moves away, it moves in plane or out of plane?
This in plane is basically stuck in the triangular point. It's all this stuff is on the z direction.
Okay.
Does that make sense?
Yeah. Okay, thanks.
Yeah, all this stuff in the direction. So in plane is basically stuck at the Vanier center in the triangular Wyckoff position. This is a C6.
Can I just interject since this is there? How do you get from what's the 1/3, 1/3, 1/2 versus 1/3, 1/3?
Very good. Very good. Well, we have a scenario. I don't know if it's a story, but we have a scenario. So the scenario is that basically, so you can see that, in fact, the phonon here is kind of flat. There's a lot of fluctuations, and it actually just starts, and if you plot it in the z direction, it's also going to be flat until it starts hitting the 1/3. When it starts hitting the 1/3, it's the 1/3 in the z direction starts popping up. So that's when you get basically. So basically, if you take a Ginzburg-Ladner of two order parameters, one at h and one at k, the fluctuations. So the one at h has a second order transition because h is equal to minus h in the third direction, not the 1/3, but the 1/2 is equal to minus 1/2. So this h point doesn't have a first order, but the k point has a first order, but the coupling between the h and the k drives the first order to the k. It's a scenario,
Okay.
but it's the only one that makes sense to me so far.
More questions? Yep.
So how will be an external magnetic field affect this electron-phonon coupling?
Sorry?
How will an external magnetic field affect this electron-phonon coupling?
Oh, well, that's a very good point. So this comes to Prin and right and what Prin and Dima's discussion, right? If you're going to have some spin, and if you have spin orbit coupling, I can think, I can add a Zeeman field. It would, if it's small field, right? If it's not orbital field, it would change the spin. Then there's going to be terms in the hopping which couple spin and orbit. When you differentiate these terms, you're going to get some, B, you're going to get some B phonon coupling, right? As if it's allowed by symmetries, right? Obviously, you have to do it case by case. I don't know how large of an effect that would be, but it's going to be there. Anything that's allowed by symmetry is going to be there, and that's how you'd get it. You just, you'd couple it to spin, then it would change the bands. When you project to a certain band, you'd have the hoppings, which vary the electron-phonon coupling projected to that band, which would change, depending on the symmetries again.